Okay, so this will be an overview, high-level overview of our software architecture for our SDK, which we call NX SDK. And what we're going to do here is I'll introduce the basic programming model that underlies our SDK. Show you how you use and program the entire system, and then once we've introduced that, we'll go over the execution model. So where do the different components and the software pieces that you write execute on our hardware stack? And then this is all covered here. And then also, how do these these software components execute in time? And finally, I'll give you another brief overview over the various API components. So what does it look like for you when you use the system, and what are some of its key features? OK, so programming model. Obviously, the SDK that I'm going to introduce here is the thing that sits in between the algorithms that you are going to write as a user of our heterogeneous hardware platform that generally consists of x86 cores, FPGAs eventually, and a lot of Loihi neural cores or our Loihi systems basically. And the general programming model behind our SDK is shown in this diagram here. So what we basically expose to you as a user are the ability to program processes that communicate via channels with each other. And specifically, there are two basic kinds of processes that we expose. Basically, these neural processes, which are essentially the neural networks, the topology, and the neural properties, and all of that, the learning rules that are executed by our neural cores. And then in addition to that, we have the sequential processes that essentially execute on our embedded CPUs all throughout the system. And they, again, communicate among themselves and with each other basically through channels. And the SDK, of course, allows you to define all these components that make up your neuromorphic algorithms. So they allow you to define these neural processes and these SNPs and the channels in between. They allow you to do state probing for debug and diagnostic to understand what's going on in your system, how your algorithm behaves. And the SDK also gives you hooks and tools to profile your algorithm, again, for debug or just understanding how much power does it consume. So we have built-in power probes, basically, so you can see as the algorithm is running, basically, how much power, how many milliwatts is it consuming. And, of course, you can measure the execution time to see how fast it's going, of course. So this is all nicely built into the SDK. And in order to understand better later on what these APIs that we're going to provide do under the hood, I'm basically trying to show you here what the computational graph is that you're programming as a user of the API. So here we have our Loihi system. And generally, using this as a representative of our entire hardware stack, we have these two types of processes running on here. We have these neural processes, which are the neural networks, the spiking neural networks. They execute on this distributed sea of neural cores on our Loihi system, and then on our various other components of the hardware stack, or on the various other CPUs, and also these embedded CPUs here at the periphery. We have these sequential neural interfacing processes, these sequential pieces of code, C code, essentially. And so, yeah, we have these processes running on here. And now, if you zoom further into these neural processes, what they really are neural networks, basically. And these neural networks, from an object model point of view, consist of other networks. So they can be hierarchical. So you can create networks out of networks containing other networks. And fundamentally, of course, on the lowest level, of terminals, neurons, and connections. So you can set up neurons, groups of neurons, and connect them with each other. And in order to connect and interface with the outside world, send data in, send data out, you can create basically terminals, or other modules basically create terminals under the hood. And if you zoom even further into this computational graph of a neural process, it will actually look like this. So this is basically a slightly more abstracted version of the the pipeline, basically, that Mike has shown on the neural core level, but again, slightly more abstracted. So at the input side, you can basically receive spikes. They enter axons. Those axons get passed on to synapses, and those synapses lead to weight lookups. And finally, these weights, the synaptic activation, will get accumulated in these compartments. Eventually, they will exceed a threshold and spike by themselves. And then those spikes get routed through these routing tables, which are essentially representing the axons to their destinations, back into the system, into other input axons. But also these input spikes could come from input terminals from somewhere outside, from a sensor, for example, or an off-chip CPU. And of course, the spikes could also go off-chip through an output terminal to a motor that it controls, or some display unit somewhere else, for example. And then for learning, we have these other elements of the computational graph, which are these pre-traces and post-traces, which keep track of previous activity on the presynaptic and postsynaptic side, and also similarly reward traces, which keep track of more global reward signals. And then we can update the synaptic state based on this type of input here. And I'll show you later how this can be used. And then what are these SNPs? So these SNPs are also relatively simple if you think about it. So basically these SNPs constitute a bunch of business logic. So you can define some sequential code in there as usual. You can write code like to do some structural plasticity, to reconfigure a network in some other way. You define all that in this body, basically. And then, as we'll show later, you also need to basically tell the system when those SNPs get executed, and then you can basically read from some of those channels and write to some of those channels, and those channels will then connect to other SNPs or to the outside world, for example. So this is the basic things that you will be creating while you program that system. And now, So these are the high-level components. So now how do they execute, and what are the actual components of the software stack? This is going to be shown in the next set of slides. So this is basically a high-level view of the software components in our software stack. And starting at the top is where you as a user would come in, for example. So you would be creating a module, for example, a vision module, a deep spiking neural network or something like this, or an LCA module, or you would just write some code up here, and they could contain some of those SNPs. So that could be neural network code, or it could be code for describing a neural network, or it could be the definition of one of those sequential processes over here. And then you would write this code using this API here, the NXNet API. That's the highest level API that we have. It's similar to some sense to PyNN or Nango, for example, in that you define populations or groups of neurons that are connected to others. And then this network specification defined in NXNet would be passed on to our NX compiler. And that compiler takes care of mapping this down to the hardware level, to the register level, which you could also directly program on if you want to. And we call this the NX Core API. But this is much harder, and there is not really a need for you to do that. But the compiler takes care of mapping a network description from this level down to that level. And generally, we provide you with a partitioner or a standard compiler to do that. But certain types of neural network topologies can take advantage of maybe known structure in your neural network, like in a CNN, for example. You don't have to solve an optimization problem to partition your network onto those many neural cores, because if there is a very regular structure, you can just compute it. So we also provide the opportunity or the possibility to plug in custom partitioners that eventually work much faster in solving this compilation problem. And then going further down below in the software stack are components that you don't necessarily need to really work with, or that you're not actually working at all with as a user, but you should be aware of that they are there and doing something in the background, just as you know that in your CPU there is an ALU processing instructions, getting data from memory and writing it back, but you don't really need to think on this level while you're writing your code. So just be aware of that these components are here. So the next level below this NX Core interface is the driver that can execute your SNPs and does a lot of system management, aggregating or across a level of basically your many maybe independent spiking neural networks. And then it's also orchestrating the NX runtime, which is the lowest level or constitutes the lowest level execution loop that drives the time step advancement of the system. So it manages basically how the system goes from one time step to the next one. And as you can see, you can run the snips that you define up here eventually at all levels of the software stack. And going further, all these snips, as I indicated earlier, can then also communicate with each other through channels. And as you can see here, in addition, those part of the SDK generally runs on our superhost, your laptop, for example. The driver would execute on the embedded on the host system, and the SNN and this NX runtime portion of the SDK, they generally run at the lowest level on the Loihi chips in the neurocores or the embedded Lakemont CPUs. And now on the next slide, or next slide here, I'm giving you, again, a brief overview over how all those various software components here shown in this static diagram execute over time, how they interact with each other and how they are scheduled. Again, just to let you know how things are working in the background. And there are 4 key features or 4 key principles of how these algorithms execute on our Loihi system. So generally, there will be nested or 3 nested levels of execution loops that execute at different time. We have, as you've seen earlier, we have channel communication between those processes across these various execution loops. And we have sequential execution of our SNN and SNPs across algorithmic time steps, and parallel execution of our SNN and SNPs within time steps. And this is now shown in this state machine diagram that I'm going to build out here very slowly so that you have a chance to follow. Okay, so when you start building a neural network, the first thing you do is, you set up your network. You define it, you specify what the topology looks like and all of that. And this will involve these pieces of the SDK. So you mostly program your network against the NXNet API, and once you're done, you would compile it on your superhost CPU. When it's compiled, the control flow is then passed on, or the control is then passed on to the NX driver and NX runtime. So the next lower level pieces in the software stack. And the NX driver will then boot up the entire system. So we go to the host CPU, we boot the host CPU. The host CPU then goes in and boots all the various Loihi chips that it manages, boots up all the embedded CPUs that are in use, and configures them. So writes the network configuration down to the system. That's this part. And eventually, once this is done, we start the overall execution once everything is finished. And then we enter the main or the next level of the execution loop, which is orchestrated by the driver. And what's going to happen here is, well, we launch the network. So we're doing a little bit more of setup configuration, and then we again pass on the control from the NX driver level on the host down to the embedded Lakemont CPUs. Which are then running in close interaction with the neurocores. So we then enter the main execution loop in the NX runtime, and what this NX runtime layer is going to do, it handles basically a couple of background processes that you don't really see as a user. So it's managing the time step advancement. So how we go from one algorithmic time step to the next. So this is happening automatically. And you just have to be aware as a user that this is going on in the background. And eventually, it's also logging like execution times if you turn on profiling of this particular feature. And then, in addition, the NX runtime is, again, while it is managing the time step advancement, what it particularly is doing, it goes through various sequential phases within an algorithmic time step. And in the beginning, there is always what we call the spiking phase. Within this spiking phase, the spiking neural network on those neurocores is active. So we update all the neurons, we produce spikes, communicate the spikes, and so on. And if you've defined any SNPs to run and to be executed in this phase, it will also be executed on one of those embedded Lakemont CPUs. And they can communicate via channels with each other. And then there are a couple of optional phases that you can eventually also go through as the algorithm executes. So if you specified any SNPs that are meant to reconfigure your neural network, that's happening in a second sequential phase after the spiking phase. So, so that is optional in brackets here. And during that phase, the spiking neural network essentially is idle. After that, if configured, we enter a learning phase. So that's happening sequentially after these two phases here. And again, if configured, you can run another management phase after this learning phase. And this would complete an algorithmic time step. And so this doesn't have to happen if you haven't specified any of these things to happen during your network setup. And the reason why these things are separated out sequentially is because a fundamental property of our mesh, basically the types of messages that we use to communicate spikes during this spiking phase between the neural cores, and the messages, the messages that we use across the asynchronous mesh to reconfigure neural cores, these types of messages cannot exist at the same time in the mesh because otherwise it could lead to deadlock. So we separate them sequentially, and they are separated by these barrier synchronization phases here in between these boxes. And so once this is complete, we wrap around and eventually move on to the next algorithmic time step until we reach some sort of termination criteria. And all the while this is happening here, all the while we are looping from one algorithmic time step to the next, the host is basically servicing all those channels that eventually those SNPs down here are using. And you also have the possibility to run further SNPs, so further custom code on your host to communicate with these channels here across these execution loops. And once you reach this termination criteria here, you would jump out, hand control back from these NX runtime execution loop back to the NX driver, where you can, again, run further SNPs if you have configured any of them. And eventually, at the end of this stage, do any state probing. So during this state probing, your neural network, again, is idle. And then if you want, you can basically probe any network state. You can probe membrane potential spikes, eventually, currents, and whatever is going on in your system, or the dynamics of your weights. And again, all the while this is happening here, the host has the possibility to log the power. So you can basically monitor in more or less real time how the power consumption is changing. And again, even on the outside layer, you're servicing channels and eventually executing SNPs at different levels of the hierarchy. And once this is done, you hand control back to the, sorry, what I missed here is, so once this is done, this again may repeat, and we may run another set of iterations of this inner execution loop. And so in the worst case, if you're, for example, probing your membrane potentials every time step, what you would do is you enter here, you go through this loop here exactly once, you go out, probe your state, and go back. And then you can see here, indicated by these different colors, in the state machine diagram over here, that basically all these things happen at different speed or at different latency, basically. So your algorithm or your neural network really runs as fast as possible if you're just running in this inner loop. As soon as you're doing state probing, you have to leave this inner execution loop and go out and involve the host, which will slow the system down. And if for whatever reason you would hand control back to the superhost and take this outer loop, the system would slow even more down. So these are just general considerations that you should keep in mind when you probe the system, use the system, and you're wondering, oh, why is my algorithm running too slow? Maybe because you're running a SNP out here that you could also be running inside of this execution loop, because then it would run much faster. But so generally, you don't really have to so beyond that, you don't really have to generally know about all of this. All you know is how you set up your network up here, and you define these SNNs and these SNPs, and you have to be aware of that they get executed by the system automatically while this entire execution loop management is going on. Okay, so this concludes the overview of the basic components of the software stack. I will conclude this part now with a brief overview of the API. So what does it look like to you as a user? Yeah.
Sorry, I'm just on the last slide. If you leave the inner execution loop and go back to the
No, you don't have to. You can basically leave the system. Of course, you can terminate everything and relaunch completely, recompile. But you can also just resume here. So you're not losing the state if you don't want to.
So it's just the internet cores are just waiting.
They are just waiting for you. They are basically waiting for you to give it another go signal.
And so no one else can.
While you're not giving up the system, it's blocked for other users. In the cloud, for example. If it's your own USB stick, your own Kapoor Bay, then of course nobody will care. It will just wait for you until you resume. But again, as you're leaving these execution loops and going out to higher levels, the execution will slow down. So do as much as possible while you ride your network. Do as much as possible in this inner execution loop, and probe as little as possible when you're running with performance in mind. Okay, so what does the API look like? So generally, the programming model behind our API is summarized on this single slide. So the first thing you do when you specify, or the fundamental way you specify neural networks in NX SDK is shown here in this first box. So what you do is basically you define prototypes for compartments, our fundamental building blocks, and connections. So you specify what a prototypical compartment should look like, what a prototypical connection should look like, and then you can instantiate these prototypes, these blueprints basically, to create actual neurons or compartments and actual connections or entire groups of them sharing the same properties. And now once you've done that, you can build networks out of these things, out of these components. So you can instantiate groups of neurons or compartments. These are depicted by these individual nodes. And you can instantiate connection groups and connect one neuron or compartment group to another one like this. So there are very simple statements in our API that allow you to achieve that. And these individual nodes here could be just single compartments or multi-compartment neurons. So then in this case, they will have some inner structure. And I'll show you a little more about this in 2 slides, what this will look like. And then you can define recurrent connections, of course. You can also instantiate input generators or spike generators, which will usually be executed or will be running on the host CPU or even the superhost CPU or on any of those CPUs. Or this software component here may just be a wrapper around, for example, a DVS camera that Ansel is later going to show you. So this DVS camera that we have over there is also wrapped inside a class or an object, which is a certain spike generator, which has these terminals, which then connect to a connection group to some piece of the network. You can create learning rules, like you can specify these equations in the sum of product formulation that Mike showed earlier. You can define learning rules and assign them to synapses or to connections in these connection groups. And another important feature is the ability to share connections. So you can instantiate connection groups, connect compartment groups with each other, but you can reuse the same for connecting other compartment groups with each other. So to take advantage of redundancy in your network topology and save resources. And you can, of course, connect your systems to the outside world, to some sort of output consumer. Could be, I don't know, robotic arm, for example. And again, this would be maybe code executing on one of the CPUs in the system. And you can define those SNPs. So you can define this sequential code performing some sort of operation, structural plasticity or whatever. And you can assign on what connection group or compartment group they are acting on, they're operating on. And of course, you can define probes to monitor the weight evolution while you're learning, or to monitor compartment voltages and spikes as they're being produced and evolve over time. So these are the basic tuning knobs and things that you can use through our high-level NXNet API. And now in the next 2 slides, I will just focus on 2 key features of the API, which is about learning and defining multi-compartment neurons. And so this is basically summarizing the learning rule API. So up here we have the computational graph, or a part of the computational graph again that I showed earlier. Synapses are, as Mike said earlier, dynamical systems by themselves, consisting of up to 3 state variables, weight, delay, and tags. And they have access to local information in the form of presynaptic and postsynaptic information that we usually denote everything that is presynaptic is denoted with X, postsynaptic is denoted with Y, and the X zeros and Y zeros are representing the spike trains on the pre and postsynaptic side, and the 1s and 2s and 3s and so on, they represent spike traces, so exponentially filtered versions of those spike trains, and analogously also for reward traces. And then you can define these learning rules in the sum of product formation, and there are different components, like you have a fundamental product. Product consists of factors. Every product is associated with a scaling factor or a scaling constant S, and then this entire block is usually gated by a dependency operator which controls whether we execute such a product at all. And then you have many terms of those eventually, and you have an epoch number that specifies how often you execute these learning rules. You could execute it every time step or every other time step. And so the way you set something like this up in the API is shown here on the right. So there's an API called create learning rule, and then you can specify strings for the different state variables, literally in that sense, basically. So you can type in a string, in this case for ESTDP, where each of these symbols corresponds to something over here. So you have these y1, x1 terms, which are these traces. So this corresponds to one of those factors. You have these x0, y0 terms. These are these dependency operators. That's this corresponding to this d. And you have scaling constants 2 and -2. That's the one over here. And so these, in this case, these x0s, y0s basically determine that we only execute this entire term if there was a y spike, or if there was a pre-spike, for example. And you can define further learning rules at the same time for the other dynamic variables, the delay and the tag. And then you can define also what the impulse and time constants are for these various traces that are used in these learning rules here. So the impulse is basically by how much does one of those pre-traces over here increase whenever there is a pre-spike, and by how much does a post-trace increase whenever there is a post-spike. And analogously for these more global reward axons that can be used. And finally, the epoch. And then this is just showing basically the same examples in this syntax here. These are basically the same examples that Mike showed earlier of the different types of learning rules that you could use, or examples of learning rules. And this is now showing a brief overview of our multi-compartment neuron API. So how do you set up one of those multi-compartment neurons that we mentioned earlier? So generally what we have objects representing a neuron. And the neuron can be visualized as a tree consisting of one or many compartments. And so at the root of the tree, you have this soma. It's just a compartment, but it's a special soma or somatic compartment. And then you can hook it up with multiple dendritic trees. Those are the blue circles over here. And then you can define operations like these yellow or orange arrows that specify how you integrate information from a child compartment into a parent compartment. These are these different join operations over here. And the way you do this is basically you can create one of those compartment prototypes that I explained earlier on the first slide about the API. You can define further prototypes with lots of configuration parameters going in here to specify these dendritic compartments or even more. And then you have like this add dendrite method where you can specify which of those prototypes you want to use to feed in as the childs into the soma compartment. And you can specify the join operation that you want to use, and you can do this as often as you want, basically. And then you can create a neuron prototype and maybe save this for later usage, or you can instantiate then a neuron out of this neuron prototype. You can do this all the time whenever you build a neuron, when you want to build a neuron prototype, or you can go to our neuron prototype library and basically import one of those predefined neuron prototypes that has been defined earlier, and then just, again, instantiate them. That is the idea behind this API here.
Is there a way to control timing or these?
No, there is no real way of controlling the timing. So when basically input spikes come in on, for example, these child compartments here, they flow through this dendritic tree in the same time step as they arrive, and then being modulated or transformed in some way by these join operations.
So is the integration instantaneous? So all of steps are instantaneous? Or?
Well, of course, in physically it's happening not necessarily all instantaneously, but every operation takes time. But for you as a user, it looks like as if it is happening in the same algorithmic time step. So a time step T, you have a bunch of spikes coming in here, and they're all getting processed, and eventually some information, depending on what you specify here, is flowing through the SOMA compartment. And then and once this is done, your algorithmic time step is over.
Yeah, but to clarify, I mean, you can specify whatever integration time constants you want, independent,
Sure.
across different compartments differently. So, that will impose some temporal, dynamics.
There's this notion of electrotonic lag. I'm just curious if you can control it. It's a duration.
Yeah, it's just you have to think in terms of the neuron model. The Kuba neuron model. You have time constants of integration that's going to delay the propagation of state to some degree, right?
Basically, each of those circles here is a live unit. And you can choose time constants and things like that to specify how they behave. OK. And then finally, last slide here is just a note on data I/O, because this is usually important. You don't want to just do some isolated computation in the system, but you usually want to send data in and out. And there are two main ways of how you can see what's going on inside the system. So one mechanism that we provide through the SDK are probes. Probes are a special object, special class in the system that are meant for automated data logging, and more specifically for debug and diagnostics, because they have a certain maybe high performance impact in some cases. And we have different flavors of probes. So there are state probes, spike probes, and then these performance, execution, and power related probes. Again, and this table shows like what the performance impact of those will be and what they can do. So with a spike probe, we can obviously log spikes, and this is relatively low cost, and there is an API. So if you have a compartment, you can just say compartment probe, and then you provide an enum, and then you will probe the spike trains coming out of this compartment. But you can also, as I mentioned earlier, probe architectural state, like membrane potentials evolving over time, weights evolving over time, and they are much more costly, because for each of them you have to go into these management phases in this sequential processing within a time step, and initiating this management phase, leading to another barrier synchronization cycle, this has a higher performance impact. So when you want to probe, be aware of probing may slow the system down quite significantly. And if you measure these performance-related things down here, they come at no performance impact. They just run in parallel to the entire system. But the way you do this is pretty similar to how you measure any of those architectural states. And so, yeah, this is meant for convenience, just for you to see what's going on inside the system. If you want to do more advanced data processing on the stream of spikes, for example, that you want to get out of the system, you would use SNPs and channels. So you would not define probes to, I don't know, control a robot, for example, because that may be slow, will be slower. So for that purpose, you would define these terminals. You would eventually define SNPs, getting data from those terminals, processing these terminals, processing these spikes, and sending those spikes into other channels out to the system, to the host that may then control a robot, for example, or the superhost, for example. Yeah, so that's meant for custom data exchange and more flexible and much faster data I/O. But it will involve a little bit more work, because now you have to actually code one of those SNPs. This is just usually a single line statement. Oh, I want to see this architectural state evolving. So that's it from the overview perspective. Are there any questions?
Are we going to see an example of what it looks like coding a SNP?
Yes, we have lots of tutorials to come.
We're not going to code a snip. We're not going to snip.
Oh, sorry, SNPs, we skipped that. We don't have a SNP example here.
What does a snip look like?
Well, again, the closest thing that I showed here is basically you define
Maybe later we can
Yeah.
flash up an example.
Yeah, I can show an
Rather than
example.
spend time now
Yeah.
trying to describe it. It'd probably be quick to describe
Okay.
it, but we should dive into the.
Okay.
Yeah. If you want to see more, that's exactly where we're going next.
Any other questions? No? Okay.
Okay, thanks, Andreas. All right, so before I go to my
You guys hear me? Yeah. All right, awesome. Okay, so let's take a quick look here before we dive into more slides. Can you guys all see this? All right, it's Christmas. Just kidding. Okay, so what we're seeing here is basically the image from the DVS camera that I have hooked up over here, right? It's going into our Kapoho Bay, which is basically that USB stick that you saw earlier that we were passing around. And that Kapoho Bay is plugged into this Linux laptop. All right? And so basically, this is the image coming out of the DVS camera. Before I go wave my hand in front of it, let me just point out one thing. You'll notice that the left side of the screen is significantly more noisy than the right side. The reason is what we did was we actually put in a very basic denoising filter in Loihi. So we're denoising the right half of the screen and not the left half. So you can see that we're actually doing processing on Loihi of the spikes in real time as it's coming through. Okay? And so, with my hand, you see me there. You can see that we're pointing at the couch back there. So, okay, any questions? It's live. Sure.
What is the denoising filter doing?
So we can go into this in more detail, but basically what it's doing is it's kind of looking at making sure that when he gets a spike, he actually thinks it's a real spike. So it's like checking if the neighbors are also spiking, because normally if the image, you're not just going to get a random spike. There's going to be a little bit of refractory put on it. So things like that tries to get rid of these random noises that show up. So, okay. All right, so with that, let me just stop this, and we'll jump back over to slides. Where is this thing?
Just waiting for your brilliant ideas to come and make something more interesting.
Yes. Is my mouse over here? This extended desktop is confusing me here.
Just go to one extreme. That's it.
Oh, there it is. It's hiding. OK. All right. Now I can bring it back. Sorry, this thing's like backwards, so I'm like trying to figure out. Very non-intuitive. There it is. OK. Come back. OK. All right. So let's keep that out of the way so we don't get distracted. OK, so let me go bring up my slides. Is the clicker over there? Yep. Awesome, thank you. Okay. Just make sure we're still alive here in terms of, I don't know if I got kicked off the network or not. Hopefully not. Okay, I think we're okay. All right. Okay, all right. So now that Andreas gave a brief overview of the architecture, and then also, more importantly, I guess for this purpose, the NXNet API, we're going to actually take a look at see what the API looks like and feels like when you actually use it. Okay, so we'll do a brief intro. Actually, let me just conclude on this DVS thing before we go forward. So just to give you a little preview of what we're talking about, right? So when we were running this DVS, what we really did is we set up this network in NXNet. So we're doing something like, as Andreas mentioned before, you have a DVS spike generator. We can connect it to a network, like your processing network, whatever you want it to be. We've just put in a basic noise filter, as I mentioned. And then we're going to connect it to some output ports, and those output ports will obviously cause the spikes to go to our host, and we can display it. So I'll come back to this example at the end after we've gone through all the pieces, or most of the pieces of this network, and we'll see the code that actually put this together. Okay? So moving forward then, so we'll start with a brief introduction just to set the context a little bit, and then we'll go into the tutorials. So specifically, we'll go through, I guess you can say 4. First one is going to be the compartments, which is basically the most kind of the basic unit that we're going to go through. It'll give you a feel of what the NXNet looks like. And then we'll build a network with learning to see how we actually do learning, use those learning rules that Andreas and Mike have mentioned. And then we'll build on top of that learning network and also add the ability to inject rewards. And lastly, we'll circle back to the DVS and see briefly what code we used to put that together. Okay, so let's go through the introduction. So just flashing this architecture slide again, here we're basically talking about the NXNet API, and we're going to use that to build spiking neural networks. And again, using this slide that Andreas used, the focus here will basically be on building Does it show up? It does. Oh, I can't see it. OK, compartments and connections with prototypes. And then we'll use those and build a network with learning as well as spike generators. OK, so those will be the focus of today's tutorials. All right, without further delay, let's jump into compartments. So as already mentioned, the Loihi compartments have various features. And in the tutorials that we've released with the NX SDK, we model some of those. And these are just a few in this particular tutorial. For example, we'll start with a very basic compartment. You put probes on it. We can do groups of compartments and have those have voltage decay. And then, of course, you can introduce stochasticity in the compartment voltage as well as refractory delay. So for this presentation, I'm going to focus on one so we can look in more detail. Specifically, we'll do a group of compartments with voltage decay. All right, so what are we going to see in this tutorial? So basically, we'll kind of see the basic flow of building a very basic network and then running it and looking at the results, right? So we're going to cover this in kind of 5 main steps. So the first is we're going to set up the compartment prototype. So the compartment prototype is basically the way to specify the parameters that you want these compartments to take. Now, once that's specified, you can actually then build the compartment using the compartment prototype. In our case, we're going to actually build a group of compartments. Then obviously, since you want to know what these compartments are doing, we can configure probes. We'll run the network, and then we can visualize it. So the plot on the right is basically what we're going to build in this example. So you'll see that in the top plot, we show the voltage curves. So there are 2 lines. One's a blue one, one's an orange one. The blue one is the compartment without voltage decay. And the orange one is the one with voltage decay. And obviously, you can see the curves are different. And based on those curves, the spiking behavior, which is shown in the bottom plot, obviously corresponds. Right. OK? All right, so that's what we're going to do. So let's jump into the code a little bit. All right, again, let's see how this extended desktop thing will do. Not showing up there. Is it on this side? There it is. Oof. This makes it difficult. I can't see the code.
Can't you just duplicate?
I can duplicate. I don't know if it's going to mess up the videoing. So that's the only question. Does anybody know? Can I try to switch over? And,
Pull out a chair and you can sit.
yeah, I might have to sit there. Let me see if I can duplicate the screen, because it'll make it a lot easier. OK, now where did this cursor go? Is it over here? OK, here it is. OK. Let's duplicate. Oh, yeah, we got to change resolution again. OK, let's do that first. Do we know what resolution was used? Does that work? All right, good stuff. OK. OK. All right, so you guys can see? Good. OK, so all right, so let's go through this. So as I mentioned, the focus is going to be on the one with compartment groups with compartment voltage decay. So this is the example. So let's just start with the code line by line, basically. So in cell 6, what we're seeing here is we have we create a network. Seth, yes?
Sorry, is it possible for you to increase the font size?
I can try to do that, yes. Let's see. If I remember correctly, it's this. All right, does that help?
Yeah.
Good enough? All right. OK, so the first thing we're doing in cell 6, basically, is we're creating this net object, OK, NXNet object. So we usually start with that to create a network. And then we're going to do the compartment prototype. So we simply do nx.compartment prototype, and now we're going to specify some parameters that we care about. This is not all the parameters. The ones that are not specified will take default values. Okay. So here we're setting up the bias term, so bias mantissa, bias exponent. So this is going to be a bias-driven compartment. And then we'll set the voltage threshold. And here in this prototype, we're basically setting compartment voltage decay to 0. And the last thing that we're setting here is the functional state. Basically, this means that we're setting the compartment in such a state that it can be bias-driven. So that's the first compartment, no voltage decay. So the second compartment prototype is the one with voltage decay. So if you look at these parameters, basically things are essentially the same. The main difference here is that we're setting the voltage decay value to a non-zero value. All right. So now we have the prototypes, so let's actually build the compartments. So that is then the next line, at the bottom of this cell, we have net.create compartment group. So we're creating a group of compartments. The size of the group is 2. All right? And since this is a heterogeneous group, we want very different types of compartments in here. We're using the list of prototypes and then a prototype map. So the prototype map is basically telling us that the first compartment is going to use, the 0th prototype, and then the next compartment is going to use the next prototype. So this way you can specify heterogeneous groups. Okay. All right. So then if we look down next, then we want to look at the behavior of the compartments, right? So then in cell 7, the first line, first code line, is basically configuring the probes. So now we simply take the compartment group. Let me just show again. So basically when we created the compartment group, we get a handle to that. It comes back, cx group. And we simply do cx group.probe. And we're going to put probes on this group. So we want to probe voltage, and we want to probe spikes, right? So that's it. So we get the probes. And then we run it, net.run, right? And then we're going to be able to see the results. So to plot them, again, the probes can plot themselves. We can simply do vprobes.plot to plot the voltage probes, and then sprobes.plot to plot the spiking probes. So I will run this so we can see. Let's restart this and clear it. All right, and then we'll run all. So we'll give it a second. Oh, sorry, I forgot that. Also, there's another mini example above, so we'll look at that in a second. OK, there, that's done. OK, so here we're running this part. So this is basically, you see Slurm is the workload manager that's running this. So we run it, and then we get the plot that we basically just talked about in the slides. Okay. Are there any questions on this example? Please. That was running on Loihi. So basically, when you do net.run, it takes the NXNet that we specified, right? It goes to the compiler, and then it gets sent onto Loihi. And basically, you see that, as I mentioned here, right, we're sending it through this is the cloud version, right? So we have Slurm managing that, and then it's sent to the Loihi board, and it's run.
Do you want to run it again there? You just scrolled up.
Yeah, sure, I can do that again.
It just looks like it did before.
Yes, agreed. Let me restart that. Yeah, I can execute the cell. Yeah, let's do that. All right, so there it's going. It's connecting, right? And then therefore it ran, and then we'd be able to plot the results again. So. Okay.
So that ran on some board over in Oregon.
Yeah.
No problem.
And so basically on the Kapoho Bay, you'd be able to run the same thing, except it'd just be local. So, okay, any questions? If not, I'll move on to the next thing. Okay. All right. It's back. Okay, all right, so we finished compartments. All right, so now that we have a basic feel for how the NXNet looks, let's build a more complicated network, and we'll also introduce learning, okay? All right, so the network we're going to build is what's shown on the screen here. So first, since we want to include learning in this, Basically, we want the ability to control the pre and post synaptic spikes. We're going to do SDDP learning. So to do this, we'll start with this top connection. So this is going to be the post-synaptic spike connection, if you will. So we create a post-synaptic spike generator, shown on the upper left. This is going to be connected by a connection, non-learning connection, okay, over to this destination compartment. So it's going to be set up so that every time we send in a spike from the post-synaptic spike generator, it's going to cause the destination compartment to spike, thus giving us the ability to control the post-synaptic spikes. For the presynaptic side, we basically have a presynaptic spike generator shown under the postsynaptic one, okay? And that will give us immediate control of the presynaptic spikes. Now that presynaptic spike generator is connected over the learning connection to the destination compartment, okay? So the question then is, well, what about this learning connection? What do we do here? So we'll see in a second that setting up a learning connection really can be done in, I like to think of it as 3 steps, right? So first, you create the learning rule. This is where you're going to specify the learning rule. You're going to specify the trace parameters and whatnot. And then for step 2, you basically will use that learning rule, and you're going to use that to build the connection. You're included in the connection prototype. Then step 3, you're going to use that connection prototype, which, as you may have guessed already, similar to compartment prototypes, is basically describing the parameters of the connection. Okay, so then you use that connection prototype, and then you build the actual connection. All right? Any questions? OK. All right, so let's take a quick look at this. Before we go to the code, let's briefly describe what we're going to look at here. So we're going to do the basic ESTDP learning. Okay, so the learning expression is shown at the top. Okay, this is basically to describe Andreas, and I think both Mike and Andreas already described this briefly. So basically, this is a weight learning. So DW means a change of weight is defined by the expression here. The C1 is just a constant, right? And then the X0 and Y0 are the pre and postsynaptic spikes, respectively. And then the X1 and Y1 are the pre and post traces, respectively. Okay. So what we're going to do is when we run this, we're going to see the plot. So the left figure, top plot, is just a straight line, because that is simply the weight of the non-learning connection. So you would expect that to not change. The middle plot, okay, are the spikes. So let's see which color is which. OK, the blue is the postsynaptic spikes, and the red are the presynaptic spikes. Right? And the bottom plot then is the weight of the learning connection. And you can see, obviously, that it is changing over time based on the pre and postsynaptic spike timings. Now, obviously, it's hard to make sense of that weight change just by looking at that time plot. So what we did was we post-process it. Basically, we look at the pre and postsynaptic time delta, spike time deltas, and then we take the corresponding weight change and we plot that in the right figure. And you can see the very basic and typical ESTDP curve. All right, is that clear? OK, all right, let's look at the code. Oops, sorry. So let me close out this one. And then we'll do synaptic plasticity. OK. All right. So this is the figure that we saw before. OK. All right. So there are quite a few helper functions in this one. So let me kind of walk through the key steps of this tutorial, and then we'll run it. So the way it's structured really is that there's this one runNet function that runs. It gets all the relevant probes and whatnot, and then we plot it. So let's first look at what runNet is doing. Okay. So runNet is kind of the high-level steps of the tutorial. So the first thing is set up network. So that obviously captures a lot of stuff, and we'll go to that in a second to look at the details of that. So basically, that sets up the network and gives us things like the spike generators. Okay. And then once we get that information, we basically generate the spike times for the pre and postsynaptic spikes randomly. So that's the next 2 lines. You see the spike times pre and spike times post. Then we add spikes to the spike generator. So this is something that you'll see multiple times if you look through the tutorials. Basically, we have the spike times, we have the spike generators. You basically add those to the spike generators, and that's at what time step these spikes will be injected into the network. We create probes in a very similar way that we did in the previous example, and then we'll run it, and then we're going to, this last extract STDP weight change function really is that post-processing that I mentioned before, where we look at the pre and post spike time delta and then look at the corresponding weight. So we can do that plot to look at and make sure that the weight changes are as we expect. Okay? So that's kind of the high-level flow of the tutorial. So I think of most interest is that setup network. So we can see exactly how we're using NXNet to set up this network. So that happens to be up here. OK, so let's walk through this. So the first thing, not surprisingly, is we create a network, NXNet. Okay? So once we have the network, we're going to create the spike generators. The spike generators are created using this net.createSpikeGenProcess call. That one argument that goes in there basically says that the spike generator is just going to have one port, meaning we're only generating one spike train. You have the ability to generate multiple ports, so you can control multiple spike trains with this one spike generator. Okay, so we have the pre and the post spike generators created. Then is our familiar compartment prototype. So we set up the compartment prototype. If we look through the parameters, the first three are familiar, I guess. We have the voltage threshold, and then we set the current decay and the voltage decay. Here, we're basically setting them to decay instantaneously. That's the maximum decay value. So, and then we have these two at the bottom, the enable spike back prop and enable spike back prop from self. So what do these mean? So excuse me. The enable spike back prop basically turns on the capability for this compartment to back propagate its spikes onto the Synaptic connections, so we can use that for learning. Right? Remember, this compartment is kind of the destination, so we want, these are the post-synaptic spikes. So we're going to back propagate that information onto the synapses. But then why do we need the second term? So the second term here, from self, basically means that when this compartment spikes, we're going to back propagate the information. But if you remember, as Andreas and Mike has mentioned, Loihi has multi-compartment features. So potentially, you can build a multi-compartment neuron where you want spikes to back propagate when children are spiking. Right? So there are other parameters that can configure that. But in this case, the simple case, when this compartment fires, we're going to back propagate that spike information back onto the Synaptic connections. Okay, all right, we create the compartment here. So notice this here, we're just creating one compartment instead of a group, so it's simply just net.createCompartment. Okay, so now let's get into the connections. So first, we're going to do the basic non-learning connection. So first, connection prototype, same concept as the compartment prototype. The parameters we're setting here are the weight, and we're explicitly setting it to learning is 0, just so we can see that. Okay, so that's the connection prototype for the non-learning connection. We then build the non-learning connection. So we simply take the spike generator, which is the spike gen post, right, the post-synaptic spike generator, dot connect CX, where CX is the compartment. And then we provide it the connection prototype. So now we've created the non-learning connection. Okay. Now let's do something similar for the learning connection. But obviously, what's different is we first need to create a learning rule. So that's done with this net.createLearningRule line. And we simply specify the learning rule. Right? This DW equals the expression that we just talked about in the slides. Right? And then we specify the parameters for the pre-traces and the post-traces. So the x1 impulse, x1 time constant are the pre-traces. The y1 impulse, y1 time constant are for the post-traces. And then we specify the t-epoch, which is basically the ability to control how often the learning engine runs. Right? Because that's what you have control over, how efficient the hardware is running. OK, so that's learning rule. Any questions on that specific point? OK, so then we use that learning rule. We put it into the connection prototype. Right? So this connection prototype is the same as the non-learning one, except we've enabled learning. Well, we set the weight to 0. OK, sorry. Set the weight to 0, but parameter-wise, very similar. Weight to 0, enable learning, and then we give it the learning rule. OK? And then we simply create the connection using this learning connection prototype. So spike gen pre.connect CX, and we give it the learning prototype. Yes?
This might be a dumb question, but the generators that you have up top,
Yeah.
green code, they're just signal generators to give some test data, right?
So for these, actually, they're defined as here. The way it's set up is that you can actually tell it what you want to send. So you'll see that. Oh, it's not in this part of the code. Basically, what we do is we explicitly give it a list of spike times, right? So these are basically, this is a very basic interface where you just give it what you want and it will send it. So you can write your own function generator if you want. Yeah.
And then there are others, for example, which work in exactly the same way, but are just giving you interface with DVS, for example.
That's right.
So just wrapping around this piece of hardware, whereas this is a pure software-based spike channel.
Yep, that's right. So when we get to DVS, we'll see basically the same idea, but with DVS. So, okay, any questions? Okay. So that covers the main thing. So let me run this again. So this one is, let's clear the output. And we'll run the whole thing, and then we can. All right, so here it's running. Okay. And then after it ran, we're plotting all the outputs. And basically, these are the plots that we just looked at. We see the weight changes, and we see the STDP, typical STDP curves. Okay. Any questions before? Yeah, please.
Where was the line of code that generated the
Oh. Yeah. So that is actually the post-processing is done over here. Okay, so basically we can, if you look in the post-processing code, basically what we're doing.
anytime you set up a probe, it's going to generate a plot.
Right, okay, so there's two things. So that SDDP curve is a special plot, right? So normally we wouldn't provide this because this is very specific to this learning rule that we can post-process to get this kind of curve, right? So that's why there's a separate post-processing function. But normally, if you're talking about just probes, basically, I guess we have a plot weight change. Let me find that here. Yeah, for example, right, as I mentioned, the probes generally have the ability to do plots. So you just do probes.plot. Now, if you want something special, you want to process it in your own way, you can obviously extract the underlying data from the probes and then do your own processing if you want. But by default, if it's like a voltage probe, compartment probe, weight probe, these basic ones, we'll just be able to plot it.
So in the special case probe thing, talk about the SDDP plot.
Yeah.
Data post-processing step.
Exactly, right, exactly. Any other questions? Okay, so let me move on to the next section.
About 8 minutes.
8 minutes, oh, okay. All right, almost there, good. Okay, so let's move on to reward injection. So if you look at this, it looks very similar to the one we talked about. Only change really is this, right? So basically we're adding the ability to send rewards into your learning, okay? So we're gonna change the learning rule and then we're gonna add some rewards. So in this tutorial, what are we talking about? So basically what we're doing is we're gonna look at the distal reward mechanism. I think Mike touched upon it a little bit in his talk, right? So we're gonna have an eligibility trace now, this DT, right, which doesn't change the weights, right, but it captures the state essentially. So this DT, this tag, is going to use the ESDP learning rule that we just talked about, except now it's going to have an exponential decay, shown as the last term. And then we have the second step, which is where we actually change the weight. So this is the DW, and then we have that dependent on the tag as well as the reward. All right? So then in terms of what we're going to see in terms of a plot, so if you look at the bottom right figure, the top plot shows the tag behavior. So this is you'll see that shortly before time step 20, the tag based on the STDP learning, it jumps and then it starts decaying. The bottom plot shows a reward. So later in time, we send a reward spike in, and that causes the reward trace to change. The middle plot then is the weight. You'll notice that the weight does not change until the reward trace actually takes on a positive value. Okay? Any question with the overall concept here? Okay, so let me jump into the code really quickly, so we can keep moving. is learning. Okay, so due to the time, I'm going to focus specifically on the pieces that are different. So this tutorial basically is the same as the learning one, only minor changes. We added a few additional auxiliary compartments just to not directly send spikes from the spike generator. We'll go through a compartment. So you'll see that throughout the code, but that doesn't change anything. But let me focus on the parts that really are different here. So the learning rule, let's take a look at the learning rule and the connection prototype. So here, again, we need to create the learning rule. So the learning rule is different from the previous one because we have the DT term now. But specifying that is pretty straightforward. We just have a DT expression, right? And then we also have the DW expression. Those two are added. The pre and post trace, the x1, the y1 parameters are still there. But since we have a reward trace now, we need to specify the reward. So we have the R1 impulse and time constant parameters there. Okay. And then in terms of the connection prototype, it's very similar to before. The weight's there. We enabled learning. We give it the learning rule. But here, because we're using the tag bits, we're going to explicitly set the tag bits to 8 in this case, just so we have it, so that we know exactly what we're doing with the tag. And then since we know this connection is going to be an excitatory connection for this example, we basically set the sign mode of that as well. Okay? So that basically is all you really need to do to enable this new type of learning rule. So then the question is, well, how do we inject the rewards? So let's go to that. All right, so it's right here. It's all lumped together with the rest of the spike generators because in this example, the reward is basically just another spike, right? So we create another spike generator process, which we called spike gen reward. Okay? It's used the same way as everything else. We add a specific time for the spike, and I think that goes to your earlier question. Here we're just saying the spike time, the reward time is what time, and we put it into the spike generator. And then we do the connection. So the only special thing here is the connection, though, is actually going into the learning rule. So the learning rule has a reinforcement channel where you point these rewards to. And so we simply do a connect to it. Spike gen reward.connect, the reinforcement channel. And now we've set up the reward. Okay. Any questions? Yeah. OK. All right, for the sake of time, I'm not going to run this one because I want to quickly go back and cover the DVS thing. That's OK. We can feel free to talk to me afterwards if we want to see more examples. But let me go to the last slide. I just want to quickly go over DVS. OK, so back to this figure, right? So we started with DVS. Let's end with DVS. So I showed this figure earlier. So now we know what the spike gen should look like. And it basically looks like what you would expect, right? We create a spike gen process, but this is a DVS spike gen process, since it is obviously a little bit different, but usage-wise, it's the same, right? So we created a DVS spike gen process, right? And then we're going to create a network. So in this example, basically what I'm doing is I'm just creating a group of compartments of size 86,400 that basically matches the resolution of the DVS camera, and we're going to connect the spike generators to it. So we build a compartment group of that size, right? And we build a connection prototype, which is just a basic non-learning default connection. We set up the identity, the mask. So what this is basically saying is that now that you have spike gen, right, that has many ports, and we want to connect it to a group that has many ports, how do you connect it? Do you connect it all to all, one-to-one? What do you want? So that mask tells us. So here we're doing one-to-one connection. And then we do a simply spikegen.connect. Okay? And obviously, you can build whatever network you want here, but here, this is just a basic one. And then to get it out, we create a spike output port group, right? So then we simply connect that compartment group that we just had to the output port, right? And that's it, right? So in terms of NXNet, that's where you get, right? So basically, with this, we take this, we compile it, it goes to the hardware, everything is set up for you. Now, what happens between the output ports and the host? So basically, the output ports are designed so that once you compile it, we set up the hardware so that the spikes are directly pointed to your host. And then what we've done in this example is on the host, we've written a snip that basically takes the spikes and displays it. Okay? So that's basically what we did to get DVS going. Right. Are there any questions? No? OK, I think that's just a video of what you guys saw earlier. So.
By the way, how many
Yes.
have we said how many tutorials we have total?
Oh, I don't think we have. We have many, actually.
So once you have access, you can run any of this, and there's probably, what do you
scroll through them.
30,
Yeah,
30 tutorials?
I can just show. In terms of Python, we have a bunch, and then we also have some non-Jupyter ones also. So here's basically a list of the ones that we have. For example, there's like a SNP tutorial that goes through that, and various other ones. But yes, sorry, question.
Could you conceivably like upload to the cloud like a data set that represents some of the event data that's coming out of the camera? Like how much data can you use in one of these generators? Because obviously you can't hook up the camera to the cloud.
Right, with the camera, using Kapoho Bay is the way to go. So I don't think we currently, I don't think we've tried uploading
There
data,
are some
but
DVS data sets
yeah.
that you can download that other people have created, and you could, for like building and testing your network, you could upload them injecting them through the software-based spike generators.
Right. That's what, so. Is there like a limit to the amount of how big of a thing that you can upload?
Well, generally, I mean, there are of course memory limits, but the way this would work is that we basically push these spikes, for example, into one of those channels, and then the data gets buffered, and you can just and eventually they get injected from one of those embedded Lakemont CPUs, and so they just read data from the channel and inject it, and so that's hidden basically from you.
Right. Right.
Yeah.
But I mean, could you? I guess like how many events would you upload? I'm not asking you to upload like a million events, but like.
Well, ultimately it would sit on the host, and that has, like by default, a gigabyte of flash memory that is limiting you, but we could plug in more flash memory.
I mean, this whole
Yeah.
system is set up to just set up channel-based streaming data. You know, it's all concurrent sequential processing and neuromorphic cores.
Yeah, I
right?
realize
So-
it's not being, the whole thing's not being downloaded from the chip. I totally realize that. I'm just
Yeah,
wondering, like,
so-
for me as a user, if I want to upload this data set, is there a file size limit?
What's the VM size we allocate?
Or the VM size. I don't know.
I don't remember. There is a limit.
It sounds like it's pretty big. I'm not going to exceed it. I just didn't know if it was like 100K or like a 1K size limit or something like that.
No, it should be bigger than that. But that's actually, one of the tutorials actually does exactly what you're describing. We load it from a file and then pump it through the network. So that is there.
So all these tutorials are organized in topics, and then inside of those individual Jupyter tutorials, you usually find many different flavors of the tutorial. Just like for the first compartment one, there are many different flavors showing different features. For example, about compartments, about learning, and so on.
Yeah.
This is what you get access to once you are in the RNSC.
Is it another tutorial other than just Jupyter?
Yeah, I mean, basically Jupyter ones are kind of the ones that have the most descriptions. There are some where, obviously, since it's Python, you can just write it without Jupyter. So there are some that are written that way.
You can go up one level,
Yeah,
then there are more.
yes, that's right. So for example, we have the NXNet ones. We even have some NX Core examples if you want to program at a much lower level, which we don't really recommend, but you can, right? So NXNet has various ones, and like, yeah. So like DVS, for example. DVS with input file, I think is what you were just asking about, right? So that's there. Okay. All right.
Okay,
Yeah,
well,
yeah.
actually,
We're right on time?
really.
Great.
So,
Thank you, everyone.
well, and hope to see you in the afternoon too, but if not,